Good evening, everybody. I'm Alex Halliday. I'm the Physical Secretary of the Royal Society, which means I'm tough and physical. So we're basically here tonight for a very special lecture, which we're really looking forward to. Before I say anything about our lecturer, I just need to say a few things. Firstly, please switch off your mobile phones or switch them to silent. Secondly, there are no planned fire evacuations. And there's a fire exit at the back there, so if in the event of fire, if the fire alarm goes off, please head towards the back and people will basically help you out. We will be using live subtitle services for the hearing impaired people in this lecture. So tonight's lecture is entitled Climate Change, Catastrophe, Hoax, or Just Lukewarm. It's being given by Tim Palmer. Switch off your mobile phones. Tim is a Royal Society research professor at Oxford University, where he leads a group exploring the predictability and dynamics of weather and climate. It may seem surprising, but Tim's PhD, also at Oxford, was in general relativity theory, where he developed the first quasi-local expression for gravitational energy momentum. He remains active in theoretical physics to the present day, particularly foundations of quantum theory and the synthesis of quantum and gravitational physics. So in case you're wondering whether you came to the right lecture tonight, Tim is best known for his many contributions to our understanding of climate dynamics, from the discovery of the world's largest breaking waves in the stratosphere to uncovering the mechanism of long-term drought in Africa. His research has consistently emphasized the role of nonlinear processes. Tim introduced a paradigm shift in the way operational weather forecasting is conducted, from best guess deterministic prediction to probabilistic prediction using ensembles of integrations. He is currently leading an EU flagship proposal on the use of dedicated exascale computers for ultra-high resolution climate simulations. Tim's work has led to the development of probabilistic techniques to forecast weather and climate, and this has been used in a number of applications, including crop yield and disease prediction. His techniques have been implemented by the Met Office and the European Centre for Medium-Range Weather Forecasting, among others. Tim has won many top awards, including the Institute for Physics Dirac Gold Medal, which is given out to Nobel laureates, etc. He has served as chair of the International Scientific Steering Group of the World Climate Research Programme's CLIVAR project. He was president of the Royal Meteorological Society from 2010 to 2012 and has been a Rothschild Distinguished Professor at the University of Cambridge during a term at the Newton Institute for Mathematical Sciences. He has sat on numerous UK government committees and in 2015 was made a Commander of the British Empire by Her Majesty the Queen for services to science. Ladies and gentlemen, please join me in welcoming Professor Tim Palmer. Thanks, Alex.
I have to say, I always get a bit worried when people give long introductions, because I worry that they probably think I don't have anything important to say, so they need to pad it out a little bit, you know. Right, I'm not going to restart my computer or install an update. Excellent. So, thank you all for coming this evening. I guess I don't really need to say that the topic of climate change has created some very polarized points of view. And in fact, let me start by reviewing a couple of those. On the one hand, we have the, let's call them catastrophists, I suppose one could say. People for whom climate change inevitably spells disaster. Now, this could be, as I say, something to do with disintegration of the ice sheets, Greenland, Antarctica, leading to tens of meters of sea level rise. It could be some contemporaneous set of droughts and heat waves in North America, Russia, South America, all at the same time, leading to a kind of mass failure of the food, of the bread baskets of the world. It could be the issue which actually was highlighted a couple of summers ago in large parts of the Middle East, where a combination of temperature and humidities, the two things together, got to the stage where it was very close to the point where human beings can't actually lose heat, either directly or through sweating. So that's a fairly existential issue. It means you have to live in air-conditioned houses for the rest of your life, something like that. Or it could be super hurricanes, things like Hurricane Haiyan that hit the Philippines a couple of years ago, producing, wind and storm surge destruction on a fairly unprecedented scale. I've sort of the reason I've highlighted a couple of books. These are not totally recent; they're a few years old now, and I'm doing it for a particular reason, which I'll come to later in the talk. But as sort of examples of the more catastrophist perspective on climate change, one could point, for example, to James Lovelock's *The Revenge of Gaia*. Like an old lady who has to share her house with a growing and destructive group of teenagers, he writes, Gaia grows angry, and if they do not mend their ways, she will evict them. So that paints a very gloomy picture about the future. And Fred Pierce's book, The Last Generation, from a similar time when Lovelock's was published, also talks about nature taking revenge in the form of climate change. All right, so that's one area. So at the other end of the spectrum, we have the hoaxists, and basically what I did there was just type climate change hoax into Google, and these are the two top hits. I guess everyone knows the famous Donald Trump tweet that its concept was created by the Chinese, blah, blah, blah. So we all know that one. The second one, I don't know, climate change is a big fat hoax, and not only that, CNN knows it. I have to say I didn't actually go into the particular article, so I can't tell you exactly what this is all about. But anyway, there are a lot of items, a lot of hits if you Google hoax. So that's if you like the other end of the spectrum. And then we have a third way, which was very articulately presented here in this lecture theatre last year by Matt Ridley, Lord Ridley, who's a well-known science journalist and in fact has a science background himself. He did a PhD, I believe, in Oxford. And he takes what seems to be a kind of a reasonable middle ground, let's say, which is that he accepts that carbon dioxide, that man-made, that climate has changed due to human emissions of carbon dioxide. So the basic notion that carbon dioxide is a greenhouse gas is accepted, that it's increasing in the atmosphere due to human emissions is accepted, that it has changed the climate, it has accounted for changes in global temperature, is accepted, but the bottom line, I suppose, is that the belief here is that the future, looking into the future, it won't really be something that is particularly damaging, particularly bad for society. So compared with all the other potential problems we have, this is not considered to be important in this perspective. And the famous phrase he came up with in the lecture is, "I am a lukewarmer." So those are three perspectives on climate change. And the question you may well ask is, well, what is the right one? Which should it be? Okay. What I want to try to do tonight is actually tell you that none of these perspectives is consistent with the basic science. So that's going to be my bottom line take-home message. And I'll try to explain as we go on why I'm saying that. So none of them is actually the right way to view the problem from a scientific perspective. So I'm going to start with my favorite, if you like, toy model of the atmosphere. So this is the famous executive decision maker, which is a little, I guess, metal ball which oscillates over four magnets, and we'll set the, hopefully this animation will work, we'll set the ball bearing, we'll set the pendulum going, and the idea is, whoops, no, that didn't work, let's try again. Yep. And the idea is to guess, you buy 10 million shares on the magnet, if you like, that the pendulum stops. So you can see it's evolving in a very irregular and clearly difficult to predict manner. It doesn't follow any obvious pattern as it goes from one magnet to the other, and well, it's eventually stopped there. So this is a good picture for how weather works. So let's think of these magnets as weather states. So let's say we'll call the yellow one, we'll call this a hot or a warm weather state. We'll call this a cold weather state. I don't know, this could be a wet weather state, and this could be a dry weather state, something like that. Doesn't really matter. Four different weather states. So as the ball oscillates around, it's describing a sequence of weather patterns. Hot, cold, warm, dry, wet and dry, so on and so forth. The irregularity is consistent with it being impossible to predict precisely where the trajectory of the pendulum will actually go after maybe a couple. You could maybe predict the first and the second one, and after that, it's difficult to impossible to predict. And the reason is that if you started the ball just minutely different, in a minutely different starting position, it would actually follow a completely different set of paths. It would follow these magnets in a completely different order. So this is a manifestation of the phenomenon of chaos, and it's what makes weather prediction so difficult out more than a day or two ahead. And some people, of course, say, well, if you can't, if weather prediction is so difficult, if it's so hard to tell us, what's happening, let's say, next month to the weather, what chance is there of us saying anything at all about, the climate in the next century? I mean, that's just hopeless, isn't it? So that's a common question people ask, and it actually, in a sense, misunderstands the nature of the climate change problem. So to illustrate the climate change problem, I'm going to do the same, run the magnets again, but now with a subtle difference. I've got this little wedge, and the wedge is going to slide underneath the pendulum, and we'll just see what happens. So if I get that animation going, so there's the wedge, and there goes the pendulum again, and again it's oscillating very irregularly, and but you can see it makes slightly more often, it's going slightly more often to that yellow magnet. The probability of it being over the yellow magnet has increased, but it does make occasional, like there, just note that, it made that occasional transition back to the white magnet, even though it was kind of being pushed away. So basically the wedge, what it has done, has taken a situation where each magnet was equally likely, they could say, because it had a 25% probability that the ball was over the magnet, and changed it to where the yellow magnet had a higher probability. I don't know, could say, let's say 50% or something rather than 25%. But even though I put the wedge underneath, the motion was still chaotic. Predicting the precise path was still basically impossible. And despite that, occasionally the magnet did make that jump back to the, let's call it the cold weather state now. My analogy is that the yellow are warm weather states and the white are cold weather states. So despite that wedge, it did make that occasional jump back to the cold weather state. Well, in some sense, the wedge is the systematically moving this wedge underneath is really representing our emissions of carbon dioxide. So these are the famous Mauna Loa on Hawaii measurements of carbon dioxide from 1960 up to the present. We know in pre-industrial times it was about 285 parts per million, and we've just relatively recently gone through the 400 parts per million. So, and really this is, I'm going to take this as a given that this is anthropogenic in nature, apart from the seasonal cycle here, which summer, winter sort of thing. So that's the wedge, that's the equivalent. So we're not trying to do a long-range weather forecast here in climate prediction. We're trying to understand how this wedge changes, which is the human carbon dioxide emissions, changes the statistics of the weather. Think of those 4 weather states. How much more likely is one, or how much less likely is another as a result of that wedge? Now, if you think of it that way, that doesn't depend on the fact. I mean, it's not made invalid by the fact that the climate is a chaotic system, but it's clearly made difficult by the fact that the climate is a chaotic system. And if you look at a time series of global temperature. So this is global mean temperature from the, say, late 19th century right through to the present. You will see it doesn't have that nice smooth increase that the carbon dioxide curve had. It has jumps. It dips down here. It dips down here. There's this famous period in the turn of the millennium where the temperature, was fairly constant for 10 or more years. Now, some people say, oh, well, do we really understand what was going on here? What was going on here? What was going on here? In my view, this is very simple to understand. We're just seeing the natural chaotic variability. We're just seeing the motion of that magnetic bob as it suddenly went back to the white weather states. Even though it was being preferentially forced towards the yellow one, it made it, it's an unpredictable system. And because it's unpredictable, you don't expect when you run, we'll talk about climate models, but when you run climate models over long periods, you don't expect it to be able to predict precisely the times when it jumps back to the white magnets, because it's unpredictable. It's part of the chaotic nature of the system. So actually, I feel we do actually understand pretty well what's going on here. We're seeing a gradual impact in the changes and the statistics of the weather, but they're punctuated by these the unpredictable and aperiodic transitions back towards, if you like, previous weather states. By the way, just very briefly, some people, we're right up here now, and some people say, yes, but we've just had an El Nino, and maybe we're going to jump back again back to colder temperatures. In the European Weather Centre, where I worked for many years, we developed a seasonal forecasting system. And I'll just show you briefly, and this illustrates something I'm going to talk about a lot, ensemble prediction. So this shows a whole load of curves which actually are spreading out enormously, but they're attempting to predict what the El Nino is going to be doing right through the rest of this year and into even into next year. And what these individual curves are saying is actually there's a lot of, it's very unpredictable at the moment what the state of El Nino is going to be. But with perhaps that one exception, all of these forecasts are predicting sea temperature anomalies in the El Nino region, which are actually positive. So there is actually a significant probability that we will actually develop yet another El Nino this year, in which case the global mean temperature, which is very much conditioned on El Nino, will actually stay high. Okay, so what's the problem then? Why are we here today? Why are we discussing, why is climate change so polarized? The answer actually is that we don't really know how thick that wedge is. Is it just slightly changing the statistic? Is it a little thin sliver of a wedge? Or is it a big, fat, thick wedge that's really perturbing in a big, big way the climate system? And the reason for that is that there are all sorts of which are sometimes called feedbacks or amplifiers, let's say, of the direct radiative effect of enhanced carbon dioxide. So let's go through some of these. Water vapor. As long ago as sort of the early second half of the 19th century, rather, the Irish physicist John Tyndall realized that actually water vapor, molecule for molecule, is probably the single most important greenhouse gas in the atmosphere. And he made the point that actually, water vapor is what stops us freezing here in the UK all the time, because water vapor, it's like carbon dioxide, acts as a greenhouse gas and traps heat essentially. So even on a day, just to be clear about this, on a day where it's crystal blue skies or nighttime where you see the stars and everything, there is still water vapor up there in the atmosphere. It's transparent to visible light, so that's why you see the stars and so on, but it's opaque to infrared heat. So the Earth, as it re-emits all that energy back in the infrared wavelengths, will trap some of that heat. Now, we all know that, as you warm the atmosphere, it can hold more water vapor. On a cold, winter or autumnal morning where the atmosphere is cooled, it can no longer hold that water vapor, and the water condenses out into droplets of water, which we call fog. But broadly speaking, as you warm the atmosphere, then it holds more water vapor. So we have an amplifier, the natural effect of carbon dioxide, coupled with our the increasing carbon dioxide levels, the increasing warming due to carbon dioxide, can amplify that direct effect of carbon dioxide. So that's one potential amplifier, one actually that we think we understand pretty well. Another one is ice albedo. So this is a picture of the Arctic Ocean, and this is the idea that as the ice starts to melt, it exposes dark water which can absorb sunlight and so on directly, rather than when it was covered with a bright white ice sheet, it reflected that sunlight back to space. So ice acts as a potential amplifier. Then we have other things like methane. The fact there's a lot of methane is yet another greenhouse gas, and that if we did start to melt permafrost and so on and so forth, that would release methane, which would then amplify the warming. Then we have yet another amplifier due to the carbon cycle. So this is the idea that, for example, as the oceans start to warm, they can't take in as much of the atmospheric carbon dioxide as they did previously, and that leaves more carbon dioxide in the atmosphere. So actually all of these things are likely to be amplifiers, but the big one here, and it's in fact it's such a big one, I'll underline it, are clouds. And this is the one thing that we understand least well about the climate system. So clouds actually have a dual role here. If you imagine the very sort of wispy, high-level clouds called cirrus clouds, which way up high in the atmosphere, sort of at the top of the what's called the tropopause region, up where the jets travel and so on. Those wispy clouds act a bit like the water vapor as blankets. They trap infrared heat. So if we, in our emissions of carbon dioxide, if we end up increasing these high-level cirrus clouds, that will act also to amplify things. On the other hand, we have the kind of more beefy clouds that we see often, unfortunately, in the UK, the sort of lower level clouds, just a kilometre or so, big thick things that completely block the sun. So I just realised it's better. I didn't switch my laptop will give up in power if I didn't do that. Okay, sorry. So we have these big, beefy stratus cloud, sort of just not very far above our heads, that acts to reflect sunlight back to space. So if climate change causes more of these, just to recall, I said if it causes more of the cirrus clouds, that will amplify the warming. But if it causes more of these low-level clouds to occur, that will actually damp the warming because it'll increase the amount of reflection of sunlight back to space. Now, I just want to show you a couple of animations of the real world, just so you understand how complicated it is. So this is a beautiful animation from satellites showing the kind of turbulent nature. We're actually looking at a water vapor channel, so we're looking at regions of moist and dry air. But you see all this swirling motion from the weather systems that propagate in both hemispheres. That's one level of complexity. Now we're going to zoom into a part of the world in the tropical Pacific Ocean. And if you look here, these are kind of thunderstorm clouds which are bubbling up from the really warm sea temperatures below. Fantastically complicated. By the way, you notice two tropical cyclones. See their little eye wall, the little centers there. But the main point about this is actually not to look at the tropical cyclones, but rather to just note, how complex these cloud structures are. These are very important cloud structures for understanding climate. As I say, thunderstorm clouds which transport a lot of heat and moisture and momentum in the vertical. So, if we're to understand this climate problem of how clouds affect climate change, we've got to start trying to model the behavior, model the complex behavior of cloud systems. All right, so let me talk about models. So we try to use the basic laws of physics, the underpinning laws of physics, to try to model or simulate the climate system, and in particular these clouds and circulation patterns that are associated with them. And I guess Isaac Newton is somewhere on the wall over there, but there he is as well with his famous second law of motion, force equals mass times acceleration. Some of you may know that. This is Max Planck, who came up with the famous formula for energy and frequency of photons. And we need that. We need quantum theory so we can represent how the sun's energy, which is obviously in the form of photons, is absorbed by the atmosphere and the land surface, and how it's re-emitted back into space as infrared energy. And this guy is Rudolf Clausius, who invented the notion of entropy. And entropy is a fundamental concept in the laws of thermodynamics. And actually, the climate system is very much a thermodynamic engine. Those mid-latitude weather patterns I showed in that animation are playing a really important role in pumping heat from the hot tropics to the cold North Pole and the cold South Pole. In some sense, that's why they're there. I mean, it affects us because it rains on us, but it's nature's way of transporting as efficiently as it can, given the kind of rotation of the Earth, the heat from the low to high latitudes. So these are the three basic kind of laws that these models that I want to talk about, the models that we use to predict climate and try to understand cloud feedbacks and so on. That's what they're based on. Now, you might think the most difficult, perhaps, is the quantum mechanics, but actually it turns out the most difficult to solve is Newton's laws of motion. And the reason is that we're not just talking about, throwing a cricket ball or hitting a cricket ball with a cricket bat and working out where the ball goes, which is the kind of schoolboy application of Newton's laws of motion. We're trying to work out how every single parcel of air in the atmosphere, and indeed every little parcel of water in the oceans, is being affected by every other parcel of air and parcel of water. So the equation that does that was discovered by Claude Navier, Frenchman, and George Stokes, another Irish physicist. And it's an equation which basically describes Newton's laws of motion, but for a continuum fluid like the atmosphere or the ocean. So this is basically the mass term, this is acceleration, and these are forces. So I've written it the other way around, not so force equals mass times acceleration, it's mass times acceleration equals force. So it's gravity, this is a pressure force, this is viscosity. The U here is fluid velocity, and the only point I just want to very briefly point out, fact that these U terms, there are two of them here together, is an indication that this is a nonlinear equation. And this is what makes it phenomenally difficult to solve. Now, I like to think of it as a work of art. In just 23 symbols, we can describe all the motions in the atmosphere and oceans from the biggest jet streams down to the air coming out of my mouth. It's all described by these 20-odd mathematical symbols. So it is indeed a work of art. But rather than this Renoir, I'm going to liken it to a Russian doll. And this is actually a very special Russian doll because it unpacks not just into 4 Russian dolls or even 8 or even 12 or whatever, or so on and so forth. It actually unpacks into billions of Russian dolls. And the reason is that if you actually want to solve, beautiful as this equation is as a piece of mathematics, if you want to solve it to get numbers out, to give to the public or to give to government about climate change, you have to unpack this equation into all these individual parts. So to actually code this on a computer, you actually end up describing these billions, potentially billions of equations. And that's what makes it so fantastically difficult. And this nonlinearity here means that energy in one Russian doll, if you imagine a Russian doll jiggling around as representing the energy in a particular scale, it kind of bashes against its neighbors and sends energy propagating up and down the spectrum in a difficult to simulate way. So in terms of the atmosphere, the biggest Russian doll, as I say, maybe is the scale of a jet stream, and the smallest Russian doll is, me talking almost. Now, even the biggest computers in the world can't represent all those scales. So what we have to do in practice to solve these Navier-Stokes equations is start to chop some of these Russian dolls, get rid of them, truncate the system to a size where we've just left with now enough Russian dolls that the computer that we have can deal with them. And typical contemporary climate models would be able to resolve scales down to around about 100 kilometers. We're kind of starting to probe less than that now, but let's say of that order. So a big, fat, juicy mid-latitude weather system is actually well described. There's a set of Russian dolls that can describe a weather system as it tracks across, say, North America or indeed the Atlantic and into the northern Europe. But these thunderstorm clouds, the one that I showed in the beginning here, the animation, are sort of beyond what currently can be represented. So we don't have computers big enough to include the Russian dolls that would actually describe the thunderstorm clouds. So we're faced with the fact that we have to represent these clouds and indeed there's a whole range of what are called subgrid scale processes which have to be represented in some way in the models. And what we do is we develop simplified approximate formulae. So this is a formula which is a relatively simple, this is a block of wood, because this is a crude thing compared to the elegant beauty of these nonlinear Navier-Stokes equations. But nevertheless, it sort of does its job to the best of its ability. Now, this T here stands for temperature, and the U, if you remember, stood for fluid velocity. This is the temperature and fluid velocity of this Russian doll here, the one next to the block. It provides the information into the subgrid formula at the smallest scale. But there's a lot of free parameters, which I've represented by the Greek letter alpha. So these are things which you have to, the formula will vary according to the parameters, but there's no obvious way in which we can set these parameters other than to appeal to observations. So we would run the model. In fact, typically what happens in a place like the Met Office now is that they would start to run their model in weather forecasting mode and see, by changing the parameters, which produces, for example, the best daily maximum temperature in London tomorrow. Because if you start getting your clouds wrong, you'll get things like your daily maximum temperature tomorrow wrong. So they do all sorts of, you could call it tuning runs or tests to see what values of these parameters gives us the best model for weather forecasting and then ultimately for climate. Now, I'm making this point because, again, a lot of people say, oh, yeah, but these models, you tune them. This is obviously a bad thing. Well, okay, fine. If we could solve Navier-Stokes exactly, we wouldn't need to tune them. But because we have these finite computers, we have no choice to get these formulae, these subgrid formulae, as accurately as we possibly can. We have to appeal to observations, and we have to see, which parameter values give ludicrous weather forecasts for tomorrow, and which ones give good ones. So I'm not an apologist for the fact that we have to use observations in deriving these models. It's just a necessary fact of the matter. All right, so let's have a look at a climate model now. So we're looking at the inside of a computer based on the laws of thermodynamics, laws of quantum mechanics, and Newton's laws of motion. And on this very large scale, it actually simulates the weather patterns extremely well. There's a lot of accuracy in these patterns that are pumping heat north. So it does that, does that very well. On the other hand, if we start to look at a bit more detail. So now we're zooming again into this tropical Pacific region, but now in the inside of a climate model. You can see it looks more like a pointillist painting than the real world. And that's because of this essential granularity, the fact that the smallest Russian doll is only 100 kilometers, and we're having to simplify the physics. By the way, just as a curiosity, this actually does produce a couple of tropical cyclones, just like the observation. But they're a kind of a pale reflection on reality. They wouldn't have the same intensity of wind strength and so on as a real tropical cyclone. Okay, so how do we take account of the fact that, when we're making, let's forget about climate change for a minute and just think about just ordinary weather forecasting. When we make weather forecasts, the fact that, the system is chaotic, we don't know the initial conditions precisely, and the models are also not precise solutions of the Navier-Stokes equations, they're only approximate solutions of the Navier-Stokes equations. So how do we deal with that uncertainty? Well, the answer is something Alex mentioned in the introduction. We run these days not just a single forecast from our best estimate of the initial conditions and our best estimate of the model. We would run a whole ensemble, as they're called, typically 50 every day weather forecasts. And the 50 forecasts would vary very slightly in terms of their initial conditions and very slightly in terms of the model equations. They'd have very slightly different, maybe formulae. These formulae, the subgrid formulae, would vary the formulae slightly or vary the parameters alpha slightly. So let's have a look at a couple of examples. This is all these are from the European Centre for Medium-Range Weather Forecasts, which you probably haven't heard of, but it's a fantastic example of a European success story based in Reading, just near the M4 motorway, where some 30-something odd countries, probably more than now, pool resources together to produce the best computer models for weather forecasting in the world, bar none. It's a phenomenally great example of what can be achieved with European collaboration. And I'd be very happy to talk more to people if they want to know more about it. Anyway, this is an example of an ensemble forecast of Hurricane Sandy, or the tracks of Hurricane Sandy, made about a week before it hit New York. So what we're seeing here are 50 different possible realizations of the initial conditions or of the model from slightly different initial conditions and slightly different model equations. So you can see from this there is a chance, based on this. So this would have been done a week before Sandy hit. One could say, well, actually, there was a chance it'll just spin off into the Atlantic like hurricanes do. But on the other hand, there's a much greater chance that it will curve back. Now, we don't know where it's going to hit, but somewhere on the East Coast, somewhere like Washington, Boston, New York, is going to be at risk. So already a week ahead, the disaster preparedness authorities can start to get into gear for a possible event like this happening. And obviously, as you get nearer the time, these probabilities become sharper and sharper. This is the famous Michael Fish. Those of you who are old enough to know Michael Fish. 1987 storm, which has been reforecast with this ensemble technique. And what's interesting actually about this example is that it kind of vindicates poor Michael Fish, because this was a phenomenally unpredictable event. Now, you probably can't see this, but we've got 50 copies here of the United Kingdom. And you see some of them have this blue thing here, which is an intense low pressure system. These are sets of forecasts about 2.5 days before the storm. So some have the low pressure system that corresponds to the storm that happened, with a very, very tight gradient in pressure, which indicates very strong winds in the south of UK. But on the other hand, many more actually have very little evidence of severe weather. So this was an exceptionally unpredictable type of situation. And this has been done with fairly much a modern-day weather forecast model, but run, as I say, retrospectively. So a modern-day Michael Fish, faced with exactly the same type of situation, the best they could say is actually, we're not sure what's going to happen, but there is about a 30 to 40% chance of hurricane-force gusts, because that actually is what, if you would look at these individual solutions, you see some of them really do have hurricane-force wind gusts in southeast England. Now, you may say, well, 30 to 40%, that's not a very large number. but it's an enormously large number compared to the kind of normal probability of a hurricane. Herefordshire, Hertfordshire, and Hampshire, hurricanes hardly ever happen, right? So 30 to 40% is an enormously large number compared to the normal probability of a hurricane. So actually, this is clearly then, again, of potentially enormous importance, again, for disaster preparedness agencies. That doesn't mean they have to suddenly deploy everything in sight, but they have to start getting ready, because if this starts ballooning up into, say, the next day to an 80% chance, okay, then at least they've started to prepare, and then so that's the way. So as I'll come to, probability forecasts are now widely used in meteorology. Some of you actually may know, when you listen to the BBC forecast, the guy sometimes says, the weather forecaster sometimes says, well, there's a lot of uncertainty, we're not really sure what's happening. And it often frustrates me when I hear this, because I don't know what people think when he says that. They're probably thinking, my crystal ball is clouded over and I haven't got a clue what's going to happen. Actually, when he says there's uncertainty, what he actually is referring to, or he or she is referring to, is that the ensemble prediction that comes either from the European Centre or from the Met Office is showing actually quite a lot of diversity of solutions, so they can't focus in on one. I'm looking forward to the day when, at least on the website, they give these probabilities as a kind of quantitative measure of uncertainty. All right, so let's move on to climate change, and I see I'm doing terribly on time here. Alex, just remind me, what time did I actually start?
What time did you start? You started about just before 2022.
Okay, fine. So I do need to speed up a bit. So IPCC so the Intergovernmental Panel on Climate Change now do similar types of probabilistic forecasts, again, varying these uncertain parameterization formulae. And these are now projections of global mean temperature with different scenarios for carbon dioxide. So very, what's often called business as usual, very strong emission of carbon dioxide with levels of up to, median levels of about 4 degrees of warming, or very radical curbing of emissions, which limits warming to much less values. But essentially the idea is that this is a range produced by these ensembles. Now, people often say, well, okay, these predictions are very much dependent on the CO2 scenario, how we go into the future emitting CO2 or not. So there's a way to express climate change without reference to our emissions. And it's a thing which has been used in the scientific community for a long time. It's called equilibrium climate sensitivity. And it's how much warming we will expect for a doubling of carbon dioxide. The first real attempt to estimate this actually came from a famous report in 1979 called the Charney Report, which came up with, based on a sort of in scientific guesswork and a certain amount of scientific examination of values of around 1.5 to 4.5 degrees of warming for a doubling of carbon dioxide. This is a much more modern type of estimate, which is actually a probability distribution. So we have different levels of warming, 1 degree, 2 degrees, 3 degrees, 4 degrees, 5 degrees, 6 degrees, 7 degrees. And this axis here is a probability. So the most probable amount of warming for a doubling of carbon dioxide, according to this pattern, according to this picture, is about 2.5 degrees. But it has this long tail. It goes down relatively slowly on the warm side. It's what's called a skewed distribution. Now, once you get certainly to 4 or 5 degrees, we are in sort of catastrophe type area. So warmings of this magnitude would certainly be associated with many of the types of things that I spoke about at the beginning. But they have, compared to this maximum here, they have smaller probability. They drop off here again on the other side, but much more sharply. So 2.5 degrees is sort of about the delineation between if you like, dangerous climate change on the right-hand side and perhaps, livable with climate change on the left-hand side. But what you see from this distribution is that the probability of it being on the left of the maximum is much smaller. It's actually about 3 times smaller than it being on the right of the maximum because it's got this skewed distribution. Okay, I want to get back to this whole issue of the lukewarm hypothesis because in recent years there's been another way. Sorry, one thing I perhaps didn't say or emphasize enough. This has all been calculated with these climate models, calculated in this ensemble mode. But in recent years, there's been a different approach to trying to estimate climate sensitivity, which is basically to say, well, here's the observations of global temperature, here's what's been happening to carbon dioxide. Can we actually determine just from these observations directly, rather than appealing to very complex models based on the laws of physics, can we estimate what the climate sensitivity is? And there was a paper in 2013 by Otto et al., which came up with a figure which is actually smaller than the climate model. Instead of 2.5 degrees, it was 2 degrees. And a further paper a year later, even pushing it down even further. And this caused a lot of discussion in the community. And in fact, if I just go back briefly to the IPCC report of 2013, particularly the Otto paper had a big influence in how this report was written, because people at the time said, well, there seems to be a bit of a contradiction or some, we can't quite square this. The observational estimates of climate sensitivity seem to be smaller than the climate model estimates of climate sensitivity. And as a result, they actually didn't give any best guess estimate of climate sensitivity, but they increased the range over the previous fourth assessment to include smaller values of climate sensitivity. Now, since the IPCC report, there's been a lot of research on trying to understand this difference between the climate models and these so-called observational estimates. And this is a paper which appeared last year in Nature, kind of reviewing actually a number of papers in turn, but making the point that actually we do understand now quite well the differences between the so-called observational estimates and the model estimates. And our understanding is such that we now think that these observational estimates should be revised upwards and resolving, as it says here, an apparent mismatch. Now, I don't have time to go through all of this, so there are 3 important areas which can explain this discrepancy. But the one I'm just going to pick up on is this third one, which is the nonlinearity of climate. I'm just going to go back briefly. In Matt Ridley's quote here, which I've taken, he says that attempts to measure climate sensitivity using real data will find that it's much lower than the models assume. Well, that very much gives you the picture of a kind of a dial on a climate model, the equilibrium climate sensitivity dial. And if you're an alarmist, you sort of crank it up to the maximum. If you're a hoaxist, you crank it down to the minimum. And if you're a lukewarmer, it's somewhere in the middle. But actually, this is not a tunable dial at all. In fact, when people run their models for the first time, they often have no idea what the equilibrium climate sensitivity is going to be. It's very much an emergent property of these models. It's not, this ECS, equilibrium climate sensitivity, is not one of these parameters alpha that I was talking about for the subgrid. It's an emergent property. So this is not a good picture to think of. But moreover, it's not only is it an emergent property, it's actually a state-dependent emergent property. So what do I mean by that? It means that if we start looking at these climate models, the cloud feedbacks actually start to kick in more as the climate warms compared to when it's cold. So the ECS is actually temperature dependent. Now, our model's doing a good job in predicting that. And there have been some interesting papers, again, in the last year or so, looking at paleoclimate data. Because now we can look at periods during glacial times and interglacial times and try to estimate how the climate responds or how it interacts with carbon dioxide during these cold periods and in the warm interglacial periods. And all the evidence indeed backs up what the climate models find, that as you start to warm the climate in the interglacial periods, you get higher climate sensitivity than in the cold periods. And this paper by Friedrich et al. Have attempted to take that IPCC curve and basically superimpose on it an estimate of global warming coming from these state-dependent estimates, these paleoclimate state-dependent estimates of climate sensitivity. And basically what they find, so the orange spread is the straight climate model, IPCC stuff, and the blue is is from paleoclimate. So if anything, actually, the paleoclimate suggests that the climate models are actually under-sensitive, that they should be warming more. Now, I'm not sure I believe that, but I think the bottom line here is that, well, in fact, the bottom line here is this, that these observation-based estimates of equilibrium climate sensitivity, it's not easy to say that, actually, they are actually consistent with the climate model estimates, providing we use enough observations. So just taking observations from the past 50 years actually isn't enough. We have to go back to periods when the climate was warm, and then we see the fact that the climate sensitivity is larger during those warmer periods. And that's pertinent then to trying to understand what will happen in the future. Okay, so scientific consensus. When we talk about scientific consensus, I would say it's basically about this distribution. It's not about individual predictions, you know, hoax, climate, or lukewarm. What the scientific community agree pretty much universally, I would say, is about this distribution. And in particular, then there's a very substantial probability of greater than 2.5 degrees, and indeed quite a non-negligible probability of even 5 or more degrees, which would be utterly catastrophic. I just wanted to say that, so I do want to criticize the lukewarm, if you like, philosophy, because it falls into the same category as the catastrophe and hoax in predicting something specific, whereas the scientific consensus is actually about this probability distribution. I'm conscious that, again, I'm running out of time, but I just want to say that in case you think I'm being explicitly critical of only about lukewarmism, I actually have written, and the reason I drew attention to those 2 books was that I wrote a review of them in Physics World over 10 years ago now, actually, criticizing them precisely for being too deterministic in the extreme sense. This phrase, the primacy of doubt, comes from a book by James Gleick on the great physicist Richard Feynman. And Gleick writes about Feynman that he believed in the primacy of doubt, not as a blemish on our ability to know, but as the essence of knowing. And so I'm just as critical of these books as I would be about the lukewarmist philosophy. So I just want to finish now, just hopefully do this in the last 5 minutes, because I've talked about making decisions under uncertainty, and I just want to give you a very simple example of how this works, and to start with weather, and we'll move on to climate, and we'll just do this in a couple of minutes. So imagine you are a consultant for Fred, the ice cream salesman, and he wants to know how many ice creams to stock up with for the next day, and your job is to tell him the temperature. And he has this curve, this so-called utility function, which will basically tell him how many ice creams he's likely to sell for a given temperature. So if it's 25 degrees, he'll sell about 70 ice creams. Okay, so your job is to not to tell him how many ice creams he's going to sell, but to tell him what the temperature is going to be. So let's imagine tomorrow the forecast is going to be based on an ensemble, so there's a probability distribution. But here the probability distribution is relatively tight. So it's going to be 25 degrees or plus or minus a degree or so. Now in this situation, it's easy to say, to calculate what the number of ice creams or the expected number of ice creams that can be sold. If you know any integral calculus, you'll know formally it's the integral of the number of ice creams multiplied by the probability for a particular temperature, and you integrate over temperature. But basically, when it's 25 degrees and there's not much uncertainty, then, okay, that's easy. So 70 ice creams. So you just tell him, okay, it's 25 degrees, Fred. He knows how many ice creams to stock up with. But suppose the next week you get something like this. Again, the most likely temperature is 25 degrees, but now there is a range of uncertainty. How do you advise him? Now, his eyes, he's going to glaze over. If you start talking probabilities, that's not going to work. So what do you do? Well, you could do a little calculation. How many ice creams is he going to... What's the expected number of ice creams going to be sold? Now, there's an important subtlety here, which is the number of ice creams increases in this nonlinear fashion. So if it's 5 degrees warmer than 25 degrees, he sells a lot more ice creams. And the increased number of ice creams when it's 5 degrees warmer is a lot bigger than the decrease in ice creams when it's 5 degrees colder, because of the nonlinear shape of this, or the sort of exponential or something quadratic shape of this function. So in this situation, the expected number of ice creams is more than 70, because if it's on this side, he sells a lot more, and if it's on this side, the temperature's on this side, he only sells a few less. So the expected number of ice creams goes up to 120. So how are you going to advise him? Well, one thing to do would be to work out what temperature corresponds to 120 ice creams. It's about 28 degrees in this picture. So you could say to Fred, plan, even though you know it's most likely to be 25, you could say plan for it to be 28 degrees. That will give you the best estimate of the expected number of ice creams sold. Okay, my colleague Chris Hope at the Cambridge Business School has done a similar calculation based on climate sensitivity. If you take this, so he's got these utility functions for global GDP, well, different regions, but GDP basically, or impact on GDP as a function of global temperature. If you take the most likely climate sensitivity of 2.5 degrees, the impact on global GDP, according to his calculation, is about $120 trillion, which sounds like a lot. But on the other hand, if you do the calculation properly, taking into account the full distribution and the fact that this curve, or these curves like Fred's ice cream curve, are nonlinear, then you actually come up with 400 trillion, which is a lot bigger. So let's imagine Fred has now given up his job as an ice cream seller, and he's become, he stood for Parliament, and he's become an MP, and he's just become the Secretary of State for the Environment. So now you need to advise him in a similar way based on these figures. And what you can do, again, is take the temperature that would correspond to an impact of $400 trillion, which turns out to be 3.6 Kelvin. And your advice to him was plan as if it was 3.6 K. So this is a way, like the ice cream and so on, to actually convert information that's fundamentally probabilistic or uncertain into potential deterministic decision strategies. So Alex, I am finished. So this is my conclusions. Projections of climate change must be based in probabilistic terms based on ensembles. I haven't talked about this, but we can look at the reliability of these probabilistic predictions on shorter timescales, days to decades. And we certainly find for temperature, the models are remarkably reliable. For rainfall, there are still some issues. The observation estimates of equilibrium climate sensitivity are actually broadly consistent with these ensemble-based estimates, but providing we take enough observations, and that probably means going into the paleo regime. So specific forecasts, they're all inconsistent actually with our understanding of climate change. We have to think in these much more, as I say, probabilistic terms. I would like to say one of the reasons for giving this talk tonight is that I hope we could maybe agree, because in some sense we do need to move the debate on to, do we want to take, do we want our politicians to take action, mitigating action to reduce these risks? I think we can only really start to debate this properly if we can agree on the underpinning science, the science that feeds into that type of decision process. So let's tonight at least agree that these climate model ensemble-based estimates of risk, they're not perfect, the models are not perfect, but they provide the best scientific means we have available for the politicians to make these decisions. Now, nobody is happy with the level of uncertainty. We do need to understand much better and get a better grasp on, particularly on these cloud feedbacks. If we're going to do that, then we've got to do two things. We've got to continue to invest in high precision measurements from space of the radiation budget and the global cloud field. And secondly, we've got to develop yet higher resolution climate models where these types of cloud systems can be resolved explicitly. And I have to say, I was utterly dismayed on Friday to get a newspaper report from the Washington Post saying that, according to a memo they have received, the National Oceanographic and Atmospheric Administration Agency, the White House is planning to cut 26% of their research budget and 22% of their satellite. We will never make any progress unless we continue to fund and do the basic research on modeling and on observation. So we need the satellites and we need the computers. So I've gone slightly over time. I'm sorry for that, but thank you all for your attention.
Well, we've got time for a few very quick questions for Tim's amazing lecture. And if you could just not go into too much of a long history in your question, just get to the point quickly so that we've got time for more people to ask questions. And if you can wait for a microphone to get to you, that would be really appreciated. But keep it very short, please. Yes, one over here.
Sorry, why is it, that's Peter, why is it called ensemble?
An ensemble is a kind of collection. So, 50 members, like a musical ensemble would comprise 50, if it was an orchestra, 50, or an ensemble is usually a smaller number, but 50 individual musicians. So here we have, let's say 50, the number is variable, individual forecasts, which together create a probability distribution.
Okay, another quick question? Yes, over here.
There's one. He's got the microphone.
All right.
Microphone. Does the last couple of slides imply we need to keep investing not just in the agencies but also in better satellite and computing technology and make sure we don't damage things like Moore's law inadvertently elsewhere?
Well, we do need to continue to invest in computing and satellite technology. I mean, don't damage. I mean, Moore's law is what it is. I mean, actually, there is an issue with Moore's. We're not going to continue. So, how we make use of this is another topic. How computers evolve and how we make best use of them is obviously very very important. But Moore's law is what it is. So we probably are at the end of Moore's law. But we'll find other ways of producing powerful computers.
There's a question over there. Yes, just here.
Thank you. Piers Corbyn, Weather Action Long Range Solar-Based Weather Forecasters. Tim, don't you have a fundamental problem that 500,000 years of real observations on the real world show that carbon dioxide levels are not a cause but an effect of climate, namely temperatures, because they're run by the sea under Henry's law. And even if you accept that that wedge you're on about is not zero, then of course you've got another problem, namely that mankind's CO2 flux in and out of the biosphere is only 4% of the total. So you've got a conspiracy of nature required by your theory, namely that man somehow dominates nature. And, for example, termites produce 10 times more CO2 than mankind. So why don't we have war on termites?
Okay.
So I do accept, actually, for understanding glacial and interglacial cycles, the interaction between the climate and the CO2 is not due to any human effect on CO2, it's due to natural effects. So that is important. But I mean, as I say, I didn't want to get into basics, but the increase we've seen from pre-industrial to present, 400 parts per million, we know this from the isotopes of carbon dioxide, that it's due to human emissions. It's one of these things that's pretty unequivocal these days.
Okay, now hang on, sorry, we've got more questions. More questions.
Bigger variations in the past.
Right, okay, let's go on to these other questions. There's somebody here in the middle.
But they're happening very quickly, Piers, by geological standards today.
Thanks very much. Why do we have jet streams? Because they seem to operate above the weather systems that you're trying to model, and they steer cyclones off in arbitrary directions and soak us all.
Yeah.
You know,
Actually, they're
how
not
do they
above.
fit
They're not,
into your?
yeah, they're not actually above. I mean, the weather, what we call weather, the weather is the rain and the clouds and everything. But the weather systems themselves, in terms of the circulation patterns, extend right up to that jet stream level. And in some sense, the jet streams are occurring. They're in a sense created by those weather systems. They're a non-linear aspect of the dynamics of weather systems. So I mean, without going into too much detail, but they are an integral part of the weather systems themselves, which do extend up to that level.
How are your conclusions applicable in daily life? Like, what kind
Sorry?
of how are your conclusions applicable in daily life? Like, what kind of position could I take if I'm in conversation with somebody about climate change? Because it seems all very uncertain.
Well, it is uncertain, but you have to think about situations that you would be in, where even if somebody, I mean, example which one might take, this is a bit silly example, but if you were about to get on an aeroplane where somebody said, the engineer said, well, we're a bit unhappy with this crack in the wing, and we think, but it should be okay. It's only a 10% chance the wing will drop off. You might think twice. Or if you had to go in for surgery, and the surgeon said, well, the risk of this going seriously wrong is 20%. I mean, then you have to decide, do I really want to go through that? So, I mean, in business every day, people have to make decisions under uncertainty. So I think our whole lives are actually, I mean, rarely do we ever make decisions where we know for sure what will be the consequences. So I think actually this is not an unusual type of situation. So the bottom line here is, if I come to that catastrophe of these, tens of meters of sea level rise, of parts of the world where humans physically can't exist, and so on, and I say to you, well, I think that is about that 20-30% probability. Is it worth us doing something to reduce that risk? Because if you think it is, the only way we're going to do it is to cut our emissions of carbon dioxide. I'm studiously avoiding trying to answer that question because I feel as a scientist, it's not necessarily my job to actually say, yes, we should be cutting emissions. I'm just trying to make the point. I'm trying to give you, if you like, the information that would allow you and indeed other people, and most importantly, I suppose, our politicians, the information in the best, as most rigorous scientific way as I can, that allows you and others to make that decision.
So, yeah, there's one more question here, and then I think we better wrap it up.
Is it accepted that 50% of Brexit voters are climate deniers?
I don't know. Maybe.
Okay. I think probably yes. Well, I think with that we better wrap it up because we could have another long discussion about that. So I'd just like to close by saying that, of course, we recognise, and including Matt Ridley, that climate change is a hugely important topic and something that science has to come to bear on and provide robust estimates for the future. And Matt, like a lot of other people, recognise that we need evidence-based decision-making. And it's actually great to see Tim explain the evidence in this way to us so that we can actually understand what it is that we're dealing with in terms of uncertainty. And trying to communicate that on the Today programme or whatever is another challenge, or to the general public in other ways. So it's not an easy thing. Tim, I think you've done a great job of trying to help us understand what the issues are and how the models are evolving. And without any further ado, I'd like to invite you all to maybe ask Tim some more questions afterwards, but right now join me in thanking him very much for a great lecture.